In this section, we'll talk about some design and analysis considerations for sequential multiple assignment randomized trials, or SMARTs. So recall that a sequential multiple assignment randomized trial, or a SMART, is just one type of randomized trial design that you can use to answer questions at multiple stages of the development of a high-quality adaptive intervention. And recall that the key feature of a SMART is that some or all participants are randomized more than once. We're going to be using this hypothetical example SMART that's aimed at developing an adaptive version of a weight loss intervention for persons with serious mental illness. The intervention is delivered at community psychiatric rehabilitation outpatient programs and involves up to 3 components: different flavors of group weight management sessions, group exercise sessions, and individual weight management sessions. And this SMART is designed to investigate various questions about whether all 3 components are needed, as well as whether and how the intervention might be modified based on weight loss after 6 months. And these questions are captured by the randomizations in this SMART. The first randomization seeks to answer a question about whether individual weight management sessions are necessary up front. The second randomization among responders investigates whether first stage treatment should be continued or stepped down. The second randomization in non-responders investigates whether the first stage treatment should be continued or stepped up. Response status here is defined as whether or not an individual has lost 5 or more pounds on their initial intervention after 6 months of treatment. Before we talk about design principles, I'd like to clear up a small misconception. Sometimes SMARTs are referred to as adaptive trials, and this is not necessarily correct. An adaptive trial is a multi-stage study in which data that you collect throughout the trial is used to modify the features or characteristics of the trial itself. So it's changing perhaps the intervention options between which individuals are randomized. SMARTs, on the other hand, are typically fixed designs. This is not always the case, but it's usually the case. All participants in a SMART typically move through every stage of the trial as it was initially designed. So the design itself is fixed in a SMART. In adaptive trials, the trial is what's adaptive. But in a SMART, we're asking questions about interventions that are adaptive. So SMARTs are designed to address adaptive interventions. It's not necessarily an adaptive trial. So let's talk about tailoring variables in SMARTs. Remember that a tailoring variable is a characteristic of an individual that you might collect over the course of treating them that allows you to inform subsequent treatment recommendations. So in our hypothetical example, our tailoring variable here is this idea of response. It's whether or not an individual has lost 5 or more pounds in the first 6 months of treatment. In SMARTs, tailoring variables are often used to restrict randomization, and by that I mean they're used to recommend different intervention options to different subgroups of participants. So responders to our initial intervention are restricted to be randomized between a continue option and a step down option. We're not interested in learning about stepping up responders, so we're not going to offer them that treatment in randomization. The non-responders, similarly, are randomized between continue and step up tactics. So we're restricting them to receive only those 2, and we're not going to consider a step down tactic for a non-responder. It's important that the tailoring variables that you include in a SMART are well justified, because remember, a tailoring variable is part of the embedded adaptive intervention. It is built into the interventions that you're studying. That means that a tailoring variable should be relatively easy to measure in situ. It should be easy for, in our example, psychiatric rehabilitation outpatient programs to assess whether an individual is a responder or non-responder, and to do so consistently. So it's relatively easy to determine if an individual has lost 5 or more pounds relative to baseline, but it may be difficult for one of these facilities to assess a tailoring variable that involves, say, lab work, involving blood draws, things like that, right? So because the tailoring variable is part of the intervention, we need to make sure that we can assess it relatively easily and systematically. There shouldn't be a lot of uncertainty in terms of who is a responder and who is a non-responder. This means that complex tailoring variables, like, for example, an individual may be classified as a responder if they exhibit 25% improvement on 7 out of 10 specific measures, is maybe not a great tailoring variable. Similarly, latent constructs are maybe not great tailoring variables. Secondary data analysis in a SMART, specifically a method called Q-learning, can be used to discover candidate tailoring variables for future work or to more deeply tailor your adaptive interventions. And so if you're unsure about whether or not a tailoring variable is a good one, it's not necessary to include one in your SMART. You can discover a tailoring variable later. Let's now talk about some primary and secondary aims, which frequently motivate SMARTs. A key design principle here is to focus on just a few scientific aims about developing a high-quality adaptive intervention. The primary aim in a SMART informs the sample size of the trial, and commonly this is a comparison of groups of experimental conditions. So when looking at that example SMART at the beginning of this section, you may have thought the sample size requirements for this type of trial might be huge. That's not necessarily the case because we'll see that we're not really comparing individual subgroups or individual experimental conditions at the end of the trial. We're comparing groups of individuals. So the primary aim should be related to scientific questions about adaptive interventions. That's another guiding principle to keep in mind. Secondary aims for SMARTs can be a little bit more fun, and they can leverage the rich data that you can extract from a SMART about treatment sequences to further inform, for example, more deeply tailored adaptive interventions. So maybe you can investigate additional tailoring variables in addition to the one that's been embedded in your trial if you've embedded a tailoring variable. Let's talk about some examples of primary aims. The first common primary aim for SMARTs that I'd like to discuss is just a comparison of initial intervention options in the context of an adaptive intervention. So here I've highlighted two groups. The first group consists of subgroups A through D, and these are individuals who, in the first stage of the SMART, were randomized to receive group weight management, group exercise, and individual weight management. So I'm going to compare outcome information from this group, subgroups A through D, against outcome information from the bottom half of the trial, subgroups E through H. And these are the individuals that started with group weight management and group exercise alone, so no individual weight management in the first stage. In the context of this comparison, a hypothetical hypothesis here might look like the following. Individuals who receive an adaptive weight loss intervention, which initially includes individual weight management sessions, will lose more weight at 18 months on average than do individuals who receive an adaptive weight loss intervention that involves only group sessions. Notice that this hypothesis is in the context of adaptive interventions, right? I'm talking about an intervention that begins with a particular set of components. And I'm averaging over future treatment. So I'm sort of ignoring what happens in the future. I'm averaging over what's happening in the future. I'm just comparing people who started with individual weight management, group weight management, and group exercise versus the people on the group-only intervention. The analysis for this primary aim is a simple comparison of subgroups A, B, C, and D versus subgroups E, F, G, and H. This is just a two-group comparison, and so I can use standard methods for this. The sample size requirements for a SMART with this primary aim are also the same sample size requirements as for a two-arm randomized trial. You can use the same formula that you would use to compute the sample size for a two-arm RCT, or randomized controlled trial. A second common primary aim for SMARTs is a comparison of second-stage intervention options among responders or non-responders. In this example, we'll consider a comparison of the options for non-responders. What this looks like is comparing pooled outcome information from subgroups C and G versus pooled outcome information from subgroups D and H. So here, I'm comparing non-responders who received the continue tactic in the second stage against the step up tactic in the second stage. So here, a hypothetical hypothesis might look like this. Individuals who do not lose 5 or more pounds in the first 6 months of a weight loss intervention will lose more weight at 18 months on average if their initial intervention is stepped up compared to if they continued on the existing intervention. So our hypothesis here is again about this step up tactic versus the continue tactic. And again, notice that this hypothesis is in the context of adaptive interventions. Right? I'm talking specifically about folks who did not respond according to a specific definition to an initial intervention. And I'm averaging over the past. I'm comparing tactics rather than specific groups of intervention components. As before, the analysis here is just a comparison of groups of subgroups. Specifically, I'm comparing subgroups C and G versus subgroups D and H. And this is, again, a two-group comparison just among my non-responders. So I can use standard methods to compare outcome information from these two groups and analyze my trial according to this. The sample size requirements, again, are similar as to a two-arm randomized clinical trial. So I can just use standard methods to get a sample size for a two-group comparison. And then to get the sample size for the entire SMART, I just need to upweight by the non-response rate. So I'll divide by the hypothesized probability of an individual not responding to that first stage treatment. Another common primary aim for SMARTs is the comparison of two embedded adaptive interventions. Remember that in this example SMART, there are 8 adaptive interventions embedded in this design. Individuals receive treatment consistent with recommendations made by up to 8 adaptive interventions. So we may wish to compare 2 of those embedded adaptive interventions on their outcomes at the end of the study. So in this example, we'll compare the adaptive intervention that initially recommends group weight management, group exercise, and individual weight management, a step down tactic for responders, and a step up tactic for non-responders, so subgroups B and D, versus an adaptive intervention which recommends group weight management and group exercise initially, then step down for responders and step up for non-responders. So this is folks who end up in subgroups F and H. In words, a hypothetical hypothesis might look like this. Individuals who receive an adaptive weight loss intervention, which begins with all 3 components, then removes individual weight management sessions for responders and increases the intensity of those sessions for non-responders, will lose more weight at 18 months on average than those who receive an adaptive weight loss intervention, which initially recommends only group components, then reduces the frequency of group weight management sessions for responders, and adds individual weight management sessions for non-responders. That's a lot of words to say that basically I'm comparing subgroups B and D versus subgroups F and H. The analysis for the comparison of 2 embedded adaptive interventions is slightly more complicated than the previous examples that we've seen. But it's still very tractable, and there's a lot of work designed around building accessible explanations of these analyses. Instead of a t-test, you may think weighted regression, so still very tractable analysis. The sample size formulae are also slightly more complicated, but they are available for a variety of outcome types, including continuous outcomes, binary outcomes, survival, cluster randomized trials, longitudinal outcomes. So there's a wide literature here on powering a SMART for this comparison. Some cleverness that I would like to highlight in this SMART design is that if we look at 2 different embedded adaptive interventions, we can see something interesting about this trial. So let's look at the adaptive intervention highlighted by groups A and C, and the one that consists of, at the end of the trial, groups E and G. So let's start with A and C. So these individuals received treatment recommendations according to an adaptive intervention that recommends group weight management, group exercise, and individual weight management initially. For responders, it recommends the same thing. And for non-responders, it recommends the same thing. Similarly, for the bottom, these folks in subgroups E and G were treated with group weight management and group exercise alone throughout the entire trial. These 2 highlighted adaptive interventions are actually not adaptive at all, because responders and non-responders both continue the initial treatment. I'm not changing anything based on response status. This means that this SMART has an embedded randomized control trial in it. This is a two-arm trial looking at group weight management, group exercise, individual weight management throughout versus group weight management and group exercise alone throughout. It's not necessary to design a SMART that includes this, but I wanted to show you that it is possible. There's a wide variety of things that you can do within the SMART framework that answer interesting questions. And so just a little bit of cleverness can take you a long way. Let's now talk about some primary aims for SMARTs that are maybe a bit more questionable, that don't do a great job of motivating the use of a SMART design. The first example here is a comparison of individual subgroups or experimental conditions. So as an example, we'll just compare the outcome information from subgroup C to the outcome information from subgroup H. Remember that adaptive interventions recommend treatments for every level of the tailoring variable. This means that an adaptive intervention is making treatment recommendations for both responders and non-responders in this context. This comparison of just two subgroups is not a question about adaptive interventions at all, because it's just looking at particular interventions received by non-responders. This is not particularly strong motivation for a SMART. This question doesn't really motivate the use of randomizing responders, for instance. It doesn't really motivate re-randomizing non-responders. So there are a lot of questions that you could address with this SMART, but this primary aim doesn't really give you a good reason to run this trial. It also makes the sample size requirements for the trial likely burdensome, actually. So this is not a great motivation for a SMART because it's not a question about adaptive interventions. Another example of a questionable primary aim might be the comparison of response rates between first-stage intervention options. It might seem that this is a question about adaptive interventions, but it's not really, because it's ignoring what's happening in stage 2. I'm sort of collecting my outcome halfway through the trial, in this case 6 months through the trial, and I'm not really looking at what's happening afterwards after I collect my primary outcome, because it's just the proportion of individuals who responded to each treatment. So it's ignoring what happens subsequently. This could be an interesting secondary analysis, but in and of itself, it's not a strong motivation for a SMART, and so it's not a great choice of primary aim. Another questionable primary aim for a SMART might be the comparison of responders versus non-responders. So you might want to say, well, how do responders to first stage treatment do relative to the non-responders? And, maybe that's interesting. This is not a great primary aim for a SMART because it's not a randomized comparison. We did not and likely could not experimentally assign response status a priori. So I can't randomize who's a responder and who's a non-responder. So this is actually not a primary aim that would motivate a randomized trial at all. It's also not really a question about adaptive interventions, again, because adaptive interventions recommend treatments for both responders and non-responders. So looking at responders alone or looking at non-responders alone and sort of comparing these two groups doesn't tell me much about how to build an adaptive intervention. So let's recap what we've learned. Sequential multiple assignment randomized trials are experimental designs which can be used to address questions at multiple stages of the development of adaptive interventions. And ultimately, the guiding principle of designing a SMART is keep it simple. This means have a tailoring variable that is easy to measure and interpretable and easy to classify. Think about a few intervention options at each stage, and focus on a few scientific aims that are really focused on the development of adaptive interventions. Because those are the primary aims of a SMART. A SMART should be designed around developing adaptive interventions. Also, sample size and analytic considerations for the primary aims in a SMART can often leverage familiar tools, things like regression or t-tests. And if you need them for more complex questions about developing adaptive interventions, more advanced methods are available to you.